Efficient sourcing of off-the-shelf supplier items such as motors and clamps can be a challenge, especially with an increasing push towards standardization for reduced costs. Also, as these are not in-house manufactured items, why spend the time and effort modeling them up for yourself? Solid Edge has some great tools to help here. To better focus on the design area of concern, we can easily change the visible parts in which we are viewing by applying a display configuration. Now, our first task is to create the gears needed to drive the wheel paddles. We can quickly review some requirement notes saved in our binder for those gear sprockets. The main benefit of the binder is that it allows you to link pertinent information to a specific assembly. Now, rather than spending time modeling them, we're going to use Solid Edge Engineering Reference, which offers a wide variety of ready-to-build engineered components like gears, pulleys, shaft, and much more from a parameter-driven interface. Just enter the pertinent information for the component you need, and Engineering Reference will analyze the calculated results and provide feedback as to whether the components are strong enough. If everything checks out, a simple click on the Create button and the components get created and placed into the assembly. You only need to provide component names. And don't forget the integrated standard parts library with optional machinery library extension. This was seen earlier in the assemble section of the first look. Perfect for standard hardware or fasteners like nuts, bolts, washers, etc. Now notice after creation, the gears are placed into the assembly where you can add specific relationships to position them. To maintain their current position with each other, we first is going to add a rigid set relationship. Another benefit of using Solid Edge when placing components in an assembly is this assemble command. This allows you to place different types of relationships from a single command. Notice here you can place multiple relationships between different parts without ever leaving the command. We also want these gears to drive the paddles. So we're going to go ahead and quickly add rigid set relationships between each of the components to achieve this. Identify the gear and then the paddle, and then the other gear and its paddle. Quickly the relationships are added. Now we can also animate the results by adding a rotational constraint, but before we do that, let's just go into the move command and make sure that these gears stay meshed and move the paddles as they should. Now for the animation, we want to add a rotational motor to one of the gears, and then once we do that, we can also set the rotational direction, and we can also change the speed if we need to. Once set, you may want to simulate the motor to test the actual results. The simulation provides you visual feedback that the gears are performing as needed. Also notice the gears driving the paddles that are connected to them. If a kinematic analysis of this motion is required, for example, to help find power requirements, this too is something that is possible. The second area that needs to be completed is on the back belt, where we have a sketch driving the length of the belt. Typically belts are purchased item and come in standard sizes. We can use the sketch in combination with GoalSeek, a tool used to optimize our in-house design for standardization. Here we need to ensure that the tensioner can cope with the standard belt length, or else the frame will have to be modified. Notice we have the tensioner in place, but as we move it, you can see that we need to lock it into position. Now, added benefit is that we can use the same sketch that drives the belt length to also locate an axial line and lock the tensioner into the correct position. The next step to getting the correct belt length is to calculate area properties within the belt sketch. Now for this, we can use the area command, which gathers area property information and places it in the variable table for us to use in our calculation. We can easily locate the perimeter once we're in the variable table, which is our current belt length. And when we find it, let's go ahead and rename it to make it easier to locate later. Also notice that we have a variable called tensioner adjustment. This is a variable that we will use to drive the length of the sketch and achieve the proper belt length. The variable table built into Solid Edge enables you to set up formulas between variables as well as variables of other components. Here we can extract the variable information to help us quickly achieve the belt length we're looking for. Now we're ready to use GoalSeek to figure out the proper length of the purchase belt for our conveyor. Notice a streamlined menu where we can first select the goal variable, then the variable to drive the actual belt length, and finally the target value we want to achieve. Simply provide GoalSeek with the appropriate values and watch Solid Edge go to work. Once it gets the belt to the proper perimeter or proper length, it's going to adjust the belt to that length, and all the parts will update as well. The final step in finishing our conveyor system is to add a couple of clamps to our frame design. Typically, these parts would be supplier purchased or catalog parts, so we can quickly source them from the Solid Edge Part Community. Now, Part Community offers access to billions of Solid Edge files. Just search by supplier, description, shape, number, size, and more. Here you can see a streamlined interface to do such tasks. Now, to take it a step further, Part Community can also find a purchasable part by matching a file you upload. For example, those gears we created from the engineering reference. And then finally, to make sure you've found the correct part, the 3D viewer can be used before downloading to Solid Edge. Powerful tools making your job simple and fast. Now, I've already done this in advance, so we will simply go get the parts from the parts library, drop them into our assembly. I know I've already mentioned the assemble command, but it is important to point out that at any time you place components into an assembly, the assemble command automatically puts you in the position to begin placement. For this clamp, we've added a mate and two alignment relationships. Anytime you place a component more than once, Solid Edge offers a tool called Capture Fit. This tool will take the relationships used to originally place a component, learn them, and then apply them on the next placement. Let's see how it works. I'm going to paste the same clamp into our assembly, and notice the from face is already highlighted. This makes component placement a snap and leaves no questions about how it should be placed. With our design complete, we can turn on all the components to see our finished product. So with the ever-challenging push towards standardization to reduce costs, you saw here that not only does Solid Edge offer various libraries, local and in the cloud, to provide pre-modeled standard and catalog parts, it also has great tools to accelerate your designs toward utilizing them.